Hi everyone, welcome back to Higher Chemistry, the bonding and properties lessons. We are on the last lesson of bonding today, which is lesson 5. We are going to have a look at the properties of some substances and use bonding to explain why those properties arise. So learning intention is to investigate how the properties of substances are affected by intermolecular forces. We'll know we have succeeded if we can use our knowledge of intermolecular forces to explain some of the properties of substances. Now, we had a look at intermolecular forces in the last lesson. This was before summer, so we'll have an opportunity to kind of revise that as well as we go along. What are the physical properties we're going to be talking about? There are 3: melting points, boiling points, and solubility. So we are going to have a look at how these properties can be explained by considering 2 things. The strength of the intermolecular forces. So this is going to mean we are going to have to look at the polarity of the molecules and the number of electrons present. Those 2 things are going to be key in helping us find out, first of all, what type of intermolecular force is present between the molecules, and 2, what is the strength of that intermolecular force. So melting and boiling points first of all. These are determined by the strength of the intermolecular forces. So remember, this is the bonds between the atoms or molecules, not inside. It's the ones that are between. When we heat something up to melt or boil it, it is these intermolecular bonds or the forces between the molecules that are broken. It's not the covalent bonds within. Unless you have a covalent network, and that is why their melting and boiling points are so high. But in the substances we're looking at today, that's kind of an exception. The substances we are looking at today, it's going to be the intermolecular forces, in other words, the intermolecular bonds between the molecules that are broken, not the covalent bonds. So here is just an example of bonds being broken. So we have 2 sulfur, 2 S8 molecules here. Here's the first one, and the second one is underneath. If we were to try and melt solid sulfur into a liquid, it's these London dispersion forces between the 2 molecules, which are represented with the red dotted line. These are the bonds that are going to break when we apply heat. The covalent bond between all of the sulfur atoms, that is an intramolecular bond. It's inside the molecule, so it does not break. Only the LDFs between the molecules is what's being broken. That's very, very important. We need to remember that. Let's look at some examples. So, does polarity affect melting and boiling point? Yes, it does, and we're going to look at these 2 examples here to find out why. So on the left, we have a hydrogen molecule, and on the right, we have hydrogen iodide molecule. On the left, we have a nonpolar molecule, so the only intermolecular force between these molecules is going to be London dispersion forces. Why? Because nonpolar molecules don't have dipoles, so they don't have slightly positive, slightly negative parts. The only intermolecular force between nonpolar molecules are London dispersion forces. As we know, London dispersion forces are the weakest type of intermolecular force, and it is this force, the London dispersion force, that is breaking when we heat this. The melting point of hydrogen is minus 259 degrees C, which is very, very low indeed. And that kind of shows how weak these London dispersion forces are. They're extremely weak. They don't require an awful lot of energy at all to overcome them. How is hydrogen iodide different then? The only difference in the molecule between these 2 is that one of the hydrogens in it has been replaced by an iodine. Now what this means is there is an electronegativity difference between the two atoms, where iodine is more electronegative, so it's going to have a greater attraction for the bonding electrons. That means that we are going to end up with a dipole in the molecule where one side has a slightly negative charge on the iodine, and the other side has a slightly positive charge, and that's going to be on the hydrogen. Now, that means that we don't just have London dispersion forces between molecules, we are going to have permanent dipole interactions. That is because we have polar molecules here, and the negative side of one molecule is going to be attracted to the positive side of the other. Now, just like before, it's not these covalent bonds that are breaking when we heat this, it's the intermolecular force, in this case, the permanent dipole interaction that's breaking here. Now, let's have a wee look. What is the melting point of hydrogen iodide? It's -50. So it's much greater than the melting point of hydrogen on its own. And the only difference is that we've swapped one of the hydrogen atoms for an iodine, but look what the difference that makes to the melting point. The fact is, and we already know this fact, that permanent dipole interactions are far stronger intermolecular forces than London dispersion forces, and that is highlighted by the difference in these boiling points here. It requires a greater amount of energy to break a permanent dipole interaction than it does to break a London dispersion force, because London dispersion forces, as we know, are much, much weaker forces of attraction. So polarity definitely does affect melting and boiling point for that reason. Next, what about the size of the molecule? Does it affect melting and boiling point? Yes, it absolutely does. We have another two examples here. We have phosphorus, so P4, and we have sulfur, S8. Now, both of these are non-polar molecules. They are made up of the same types of atom, which means they won't have a permanent dipole. They won't have a slight positive side, slight negative side. There is no difference in electronegativity, so we have non-polar bonds and non-polar molecules. Now, what that means is, in both of these circumstances, in both of these examples, there is only London dispersion forces, which are between molecules. And these are represented again by the dotted red line. So here they are between the phosphorus molecules, and here they are between the sulfur molecules. Now, when we heat these substances, it's going to be the London dispersion forces that break. We know that already. What we're interested in is what are the melting points and boiling points, and does the size of the molecule affect it? Well, yes, it does. Phosphorus's melting point is 111 degrees C. It only has 4 atoms in the molecule, whereas sulfur has 8 atoms in the molecule. So sulfur contains far more electrons and is a larger molecule than phosphorus. So we can then predict that sulfur's melting point is going to be higher. And in fact, it is. It's 115 degrees C. But you might be thinking, well, there's only 4 degrees of a difference. That's not very much, and you'd be absolutely right. There is only 4 degrees of a difference, but that just shows you how weak the London dispersion forces actually are. Last time when we compared polarities, so we had London dispersion forces against permanent dipole interactions, there was 200 degrees of a difference, give or take. This time we only have 4 degrees of a difference, and that's because London dispersion forces are very, very weak. Yes, they increase as the molecules get bigger, but it's not the greatest increase. It's not anywhere near as large an increase as it is when we move from London dispersion forces to permanent dipole interactions to hydrogen bonding, for example. So, the key thing to remember is, yes, the size of the molecule does affect melting and boiling point. As the size of the molecule increases, so does the number of electrons, and therefore the London dispersion forces get stronger. We need more energy to break these London dispersion forces down, so the melting and boiling points are higher. Now, in your notes, you have this really handy table which tells you if you have this type of bonding in a compound, here are the bonds that are broken. And it's decreasing strength of bond and melting and boiling points. It starts off with the strongest bonds and then slowly goes down until we get to LDFs at the bottom. So covalent networks, I told you kind of earlier, that's a wee exception. And when we try to melt or boil, melt a covalent network, it is the covalent bonds that we are trying to break here, but that's the only exception of that. If we have ionic bonding, then it's the ionic bonds that are broken. We know that already from National 5, hopefully. Metallic, it's your metallic bonds that are being broken. If you have polar covalent molecules, then if they have hydrogen to NOF elements, nitrogen, oxygen, or fluorine, it's going to be hydrogen bonds, and they are strongest, remember. If you have any other elements, you're just going to have general permanent dipoles. Non-polar covalent molecules have only LDFs, and monatomic, like your noble gases, have only LDFs as well. Now, I think it's a key part to know. A key thing to know is that even though we talk about how strong hydrogen bonds are, hydrogen bonds are the strongest intermolecular bond. They are not the strongest bond. Covalent bonds are the strongest bonds. So covalent, ionic, and metallic bonds are your intramolecular bonds. They are between atoms. They are extremely strong. Hydrogen bonds are your strongest intermolecular force, then permanent dipole attractions, and then London dispersion forces. So this table kind of highlights that in a nice order here. But just remember on this kind of line here that hydrogen bonds are a strong type of permanent dipole interaction. Okay, so we have had a wee look at melting and boiling point. Our next property is solubility. And there is a really, really simple and easy way for you to remember the solubility of any type of compound, and it is like dissolves like. So similar things will dissolve each other. If you have polar molecules, you're going to want a polar solvent to dissolve them in. And conversely, if you have a non-polar molecule, you're going to want a non-polar solvent to dissolve them in. Really straightforward if you just remember that like dissolves like. I've just kind of said that. So this is the reason why oil and water don't mix. Oil is a long chain kind of hydrocarbon. It has carbon to hydrogen bonds, which we know are non-polar. So it's a non-polar solvent. It's not going to mix with something that's polar like water because they are completely opposite types of substance. So some examples then. Ionic compounds and polar molecules will dissolve in polar solvents. So polar solvent examples, water or ethanol are my go-to polar solvents. Non-polar molecules will dissolve in non-polar solvents, like hexane's probably my go-to non-polar that I think of, or tetrachloromethane as well is going to be a non-polar solvent. You might be thinking, why have you brought in ionic compounds? Well, we have to think of ionic compounds based on what's going on inside. So they contain ions, remember? The ions are held together by ionic bonds. But these ions have charges, so they are very similar to polar molecules in that they both have charges. So if you try to dissolve an ionic compound in water, as we know from National 5, the water molecules will rip apart the lattice, but it's because of the charges. The charges in the water molecule will be attracted to the charges in the ionic lattice, and that will help to break it up, and that's why they dissolve so easily. Water It's quite interesting. It's one of the few substances where the solid form will float on the liquid. And just for kind of knowledge, this is in your booklet as well. In the liquid state, there is no kind of nice arrangement. They are all held together by their hydrogen bonds, but it's very kind of messy looking and unstructured. When we freeze water, so when it reaches the solid state at 0 degrees C, the hydrogen bonds become much more stable. They spread out from each other, all of the little molecules, and are in a much more stable arrangement, as you can see in this diagram here. Because the molecules push away from each other in the solid state, this makes the solid less dense than the liquid, which means it will float on top. So we wanted to use our knowledge of intermolecular forces to explain some of the properties of substances. We are going to now attempt the questions. These are on page 13 of your booklet. There are 5 questions, I believe. So as usual, have a look at the questions, see if you can attempt them, and then come back and watch the video and self-mark your answers. So here they are. Like I said, they're on page 13. And we will go ahead and answer some of the questions. So, 11. Which of the following would have the highest boiling point and why? So, we have iodine, bromine, and hydrogen. All of these are diatomic elements. They are all therefore bonded to an atom with the same electronegativity. So they are all non-polar. So if they are non-polar, that means that they are held together by London dispersion forces. So if we have 3 substances, or all of the substances are held together by London dispersion forces, the thing that we need to look for then is which molecule is the largest. Which molecule has the largest number of electrons? That molecule is going to have the strongest London dispersion forces and therefore the highest boiling point. So if we have a look here, hydrogen has the smallest number of electrons. It only has 2 in a molecule. Bromine has more than hydrogen, but iodine has the highest number of electrons. So that means iodine is the largest molecule with the strongest London dispersion forces and the highest boiling point. You will get 1 mark for talking about how iodine has a greater number of electrons than bromine and hydrogen, and the other mark will come from stating that it has the strongest London dispersion forces and therefore the highest boiling point. That's where your 2 marks will come from. 12. Explain which bonds are broken when the following substances are heated past their boiling point. So we're having a think about which intermolecular forces these substances are going to be held together by. Now, phosphorus atoms are going to be held together by London dispersion forces. Why? Phosphorus bonded to phosphorus, we're not going to have any difference in electronegativity. It's a non-polar molecule, so that means it's always going to be LDFs. Neon is a monatomic element, which means, again, we're only going to see LDFs here. We've got no dipole, no polarity, nothing. Ammonia, NH3, so if you have lots of ammonia molecules together, you are going to have a dipole created. This is a polar molecule where the nitrogen is going to be slightly negative, the hydrogens are going to be slightly positive. And what this will do is this will hydrogen bond. So the positive hydrogen of one ammonia molecule is going to be attracted to the negative nitrogen of the other. So that's going to be hydrogen bonds that are broken in that instance. It might be really helpful for you to draw these out. That is what I usually do. If I have a question about bonding and it's asking about intermolecular forces, I will go ahead and draw out each molecule just to be absolutely sure and not to rush it too much. So just take your time, draw out the molecules, make sure you know if they have a dipole or not. Hydrogen chloride is going to have a dipole because it has a difference in electronegativity. So it doesn't have any hydrogen bonding. It hasn't got hydrogen bonded to nitrogen, oxygen, or fluorine. So it's simply going to be a permanent dipole interaction. So you're going to have the positive side of the hydrogen attracted to the negative side of a chlorine in a neighbouring molecule. And lastly, carbon tetrachloride is going to have polar bonds because you've got a difference in electronegativity. But the way it is arranged, you have the four chlorines surrounding the carbon. So you're going to have an overall non-polar molecule. So between those molecules then, it will just be London dispersion forces. And that's 1 mark each for that. 13. So this is a 3-mark question, which means we're going to need 3 valid points for full marks. So chlorine's boiling point is much higher than the boiling point of argon. Explain why this might be. So 3 points here. First one, argon is monatomic, chlorine is diatomic. So we're going to see quite a difference in the size of the molecule. In other words, the number of electrons. So 1 atom of argon is floating around by itself, has 10 electrons, whereas 1 molecule of chlorine contains 34 electrons. Remember, if you're looking for the number of electrons of an atom of an element, go to your periodic table. It is the same as the atomic number. So that's your first point. Chlorine contains more electrons. Both molecules are non-polar, so will both only contain London dispersion forces between the molecules. The bigger the molecule, the more electrons present, the stronger the London dispersion forces. That's mark 2. The third mark is going to come from saying that the stronger the London dispersion forces, the more energy required to break them, and therefore the higher the boiling point. So that is why chlorine's boiling point is much higher than argon's, because it has stronger London dispersion forces. So that's mark 1, mark 2, and mark 3. Don't just assume that the marker knows exactly where you're coming from. A really good tip when you're writing 3-mark questions, either questions like this or using your knowledge of chemistry, is pretend that the marker knows absolutely nothing about chemistry. Pretend you're writing this so that somebody, like your friend, your family, can understand it, somebody who knows nothing about chemistry, and that way you'll really explain everything that you know, because sometimes we all fall into the trap of just assuming the marker knows what we're talking about, so we kind of trail off and don't explain things as well as we possibly could. So bear that in mind for these questions. It's so important to explain how you know what you are writing so that you get maximum marks. Okay, 14. Which of the following molecules is most likely to be soluble in water and why? So here we're going to have to look at each individual molecule, find out its polarity, and see how that compares to water. Now remember, water is a polar molecule and like dissolves like. So we are going to be looking for the most polar molecule here, and it's going to be the most soluble in water. So I have drawn these out. The first one, phosphorus trihydride, has non-polar bonds. Phosphorus and hydrogen have the same electronegativity, so therefore we have a non-polar molecule. So it's not going to be A, because like dissolves like, water is polar, phosphorus trihydride is non-polar. They won't mix. Next, we have carbon dioxide. Now, if we draw it out, we can see that we do have differences in electronegativity. So we have polar bonds, but the arrangement of these atoms within the molecule make it a non-polar molecule. We don't have a clear positive or a clear negative side. So again, it's not going to be carbon dioxide if it's a non-polar molecule. That leaves us with hydrogen chloride, which we can just check is a polar molecule because it has a clear negative side at the chlorine and a positive side at the hydrogen. So the most polar molecule of the 3 is hydrogen chloride. It's going to be the most likely to be soluble in water. So in my explanation for the 2 marks, I've put phosphorus trihydride and carbon dioxide are non-polar molecules. Water is a polar molecule, so is hydrogen chloride. Now that's an important piece of information to get a mark from, because the question says most likely to be soluble in water. It doesn't actually tell you that water is a polar molecule. So if you're right that you know that water is a polar molecule and so is hydrogen chloride, then you are definitely going to get that mark. The second mark will come from saying like dissolves like. So the polar molecule is going to dissolve in the polar solvent, which is water. Last one, this is another 3 marker here. Now it says explain the difference in solubility of methane and hydrogen fluoride. So that's just wanting us to demonstrate our knowledge of solubility and of the polarity of molecules. So what is the polarity of methane? What is the polarity of hydrogen fluoride? And therefore, what kinds of substances are these going to be soluble in? That is what that question is asking. So I have drawn out both of these molecules. Methane, as we know, is a non-polar molecule. The carbon to hydrogen bond is non-polar. So we have methane as a non-polar molecule, and then hydrogen fluoride. Fluorine is extremely electronegative, so it has a delta negative. Hydrogen has a delta positive. We therefore have a polar molecule. So a wee bit of explanation then. A molecule such as methane, which is a non-polar molecule, will dissolve in other non-polar solvents. So for example, hexane. Now I would definitely put an example in here. And as I said before, hexane is my go-to for a non-polar solvent. It's just one that I find it easy to remember. On the other hand, a polar molecule like hydrogen fluoride will dissolve in other polar solvents, for example, water or ethanol. Again, those are my go-to polar solvents. And this is because like dissolves like. So that's definitely going to be enough to get your 3 marks. By stating what the molecules are, I would definitely draw them out and draw in your little delta positive and negatives to show the polarity of the molecules, and also explain with examples some of the solvents they would be soluble in. That's going to get you your maximum marks. So that is it. That is all the questions answered. Let us know how you got on with that. And as always, please upload a little picture of your self-marked solutions. And hopefully everybody has a great day and a great week. Thanks for watching.